Bond.
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 My name is Bond.
My name's Bond.
It's Bond.
Bond.
My name is Bond.
The name's Bond.
Bond.
Bond. Bond.
The name's Bond.
In this video, we're going to look at ionic bonding. So just to recap from what we've seen before, we're going to look at the electron shells. So we said that the electrons orbit around the nucleus of an atom in those distinct shells, and we've only ever talked about 3 shells, and we said it's a 2882. Sorry, so that's 4 shells, not 3, 4 shells, 2882. One of the weird things that often confuses students is that when you only consider 4 shells, so up to about the 18th element on the periodic table, it works out perfectly in just going 2882. However, in reality, the shells actually go 2818 2. And why that's a little bit strange is that what happens is the electrons fill up that third shell to 8. Then they start filling up the next shell. And then that can actually get more than 2. But again, it starts filling up the next shell. Once that next shell is full enough, it then goes back and starts filling up that 8 again all the way up to 18. Then it jumps back to the 4th shell and keeps filling it. So it's actually a lot more complex. But because we only ever deal with sort of the first 20 elements, the 2882 rule works, because up to that 20, you've only got 2882. But as you get further along the periodic table, jumps back and that third shell can actually hold more than 8. So just keep that in mind, but for us it doesn't really matter because we're only dealing with the first 20. As we've said before, the valence shell, which is that outer shell of electrons, it wants to be full. If it can't be full, it wants it to be empty and just get rid of it entirely so that the next shell in can be full. And that's the goal of an electron. It's the sole purpose in life. In order for it to do this, it's either going to donate or gain electrons to either fill its shell or to give away the few that it's got to empty that shell. Where this is really useful is that we can almost look at a periodic table and we can identify from it what kinds of things are going to react. For example, if we look at 2 elements that both want to give away electrons, they're clearly not going to react with each other because they don't support each other. They both just want to get rid of things. No one's actually buying, everyone's selling. Whereas if we find an element that is giving away to, and we find an element that wants to, there is a very good chance that they're going to bond in some form, or they'll react, or they'll do something, but generally they'll bond. So with this power of groups and periods on a periodic table, and recognizing what ions they'll become, we can figure out what kinds of things are even going to react in the first place. So it's really the periodic table is actually a very powerful tool. That last column, our noble gases, all have full shells. So they are not going to react with anything. They don't bond with anything. They don't do anything. They are happy. They're not going to give away their full shell. They're certainly not going to take more because they've got a full shell. So chemical bonding. It's the process of an atom sticking together. And that's sort of not the technical term, but it's a great way to think of it. When we create a compound, it's because there is a chemical bond there. It's one of the fundamental components of chemistry that explains all of the molecules and compounds that we've talked about. Now we're actually going to see how are they stuck together. What is the bond that holds them together? Such as our carbon dioxide, carbon with 2 oxygens. It actually looks something like this in this picture, and we'll explain this. So remember, we're talking about the periodic table. The alkali metals are this group 1 column. They have 1 valence electron. The alkaline earth metals of group 2 have 2 valence electrons. So on and so forth. If you remember, it goes like 1, 2, and then it goes like 3, 4, 5, 6, all the way up. This is then 13 in the new system. In the old system, they skip the middle, and as they do here, just go 1, 2, 3, 4, 5, 6, 7, 8. So either way, this is going to end in a 3. It's either 3 or 13. But these have 3, these have 4, these have 5, etc. So if we look at it, depending on where it is, if it's only got 1, and it's only got 1 shell, does it want to get rid of it? It's going to take 1. It's easy to take 1 in this case. If it's got 1 in the outer shell and it's the second shell, so that's the 8, so the 2, 8, it's much easier to give that away. So these things are going to give away electrons more likely. If we've got 6, even 5, but 6 in the outer shell, we know we want 8s, they're going to take. So they're going to take 2, you're going to take 1, happy, not going to take anything. Ionic bonding occurs when an element donates its electron. So it's really that donation process. One of them will take an electron, one of them will gain an electron, that forms an ionic bond. They don't just take it and off they go and they're happy now and lithium is now charged and fluorine's charged. No, they stick together. It's electrostatic. And it's just like we talked about when we formed ions in the previous module. If an element gives away its electron, it now becomes more positive. But if it gives it to another element, that element will become more negative. And a positive and a negative are attracted, just like the north and south of a magnet are attracted, opposite charges are attracted. So the things are now stuck together because of the fact that they're opposite charges. And this forms an ionic compound. So this is the bond, it's an ionic compound. To write the formula for an ionic compound, we first identify what the cation is. So remember, cats are positive. So which of these ions is becoming positive? It's written first. The cation is always written first. Then write the correct formula and the charge for the cation. We then identify what the anion is. The anion, which is the negative ion, remember, like a negative ion, anion, that's written last. Then we write the correct formula and the charge for that anion. So when we're talking about correct formula and charge, we're talking about, well, what's it done? If it's a negative ion, it's gained electrons. Is it a 2+, 3+, etc.? That's what we're talking about, changing the right symbols for the charge. Then we combine the cation and the anion, and we need to produce electrically neutral compounds. So that's important. If you identify that one of them is going to become a, let's say, 4-, for example. It's taken on 4 electrons. It's going to become a 4-. But the other thing is only a 2+. It only gives away 2. Then how does that work? How is the whole thing neutral? You must have had 2 of that thing. So like a CO2, for example. The C would want 4 maybe, but the O's will only give 2. So you need 2 of them. So that's where our CO2, for example, comes in. So that's how we identify. This is the only time when we're writing these ionic compounds that will change the subscript. So like a CO and then we put a 2. Remember in the balancing, we only ever touch coefficients. Now you're given the power, the freedom to change those subscripts. So remember, if they're not equal in magnitude, use the charge of the cation as the subscript, the charge of the anion as the subscript to make those things electrically neutral. Then when we look at the actual chemical equation, we can balance it from that point. So let's look at an example. We react sodium and fluorine. Sodium, we write out its electronic configuration, 281. Fluorine is 27. So sodium is going to become Na+, and it's 28 now. And fluorine will become F-, and it's 28. So sodium has given up its outer shell, given it to fluorine to fill its outer shell. Na and F- are going to join to form NaF. It's electrically neutral because it was a +1 and a -1. So sodium fluoride is our neutral compound. Have a go at these examples. Magnesium and oxygen. Calcium and nitrogen. From here, there will be a practice worksheet on ionic bonding, and next lesson we will look at covalent bonding. I'll see you then.